Hello, everybody. Thanks for joining us here. And I know that there's been a lot of interest in machine learning related things. This summit, 2 years ago, it was Delta. Last year was streaming. So this time it's more about machine learning more than anything else. And I think it's important to highlight use cases that drive value for the business. And I'm glad that this session is one that's likely in production. And we have Aayush Patel, a data and platform engineer at SkyWatch, who's going to be delivering this talk on a very important topic that I think would be of interest to you. So let me just hand it over to him. Thank you.
Thank you. Thank you all for being here. It's so great to see you all in person. It's really fascinating to see how data can unlock valuable opportunities and create positive impact across all industries. My name is Aayush, data and platform engineer at SkyWatch, a company whose mission is to democratize Earth observation data. And today, I would like to share our journey on how we were able to transition from generating insights to predicting demand for satellite images and generating recommendations, and finally turning them into monetizable actions. So let's do a quick exercise first. Can you please raise a hand if you are using satellite images at your job? Cool. And how many of you are actually working with geospatial data? Nice. So for those who are actually not working with geospatial data, I would actually like to use the famous quote, which is, everything that happens somewhere. So there is always a geospatial component, no matter what industry you are coming from. There are thousands of satellites orbiting our planet Earth that captures enormous amounts of information that makes our lives better. At SkyWatch, our mission is to make it easy for everyone to access Earth observation data. Accessing satellite imagery has been challenging for many years now. It was difficult, it was expensive, and time-consuming. In 2018, SkyWatch released its first product, EarthCache, which abstracts all the complexity and allows customers to access satellite imagery with just one post and one GET API request. On the other hand, if you're a satellite operator, there are many things that you worry about, from building a satellite and launching it to space. Data infrastructure is not normally at the top of the list. And sometimes it's the last-minute thing that you decide on how you will actually monetize your data. TerraStream solves that problem by taking care of data distribution, data management, and data processing, and helps you monetize your data very quickly, especially through its integration with EarthCache. Think of it as a Shopify for Earth observation. So with EarthCache and TerraStream, SkyWatch makes it easy for everyone to access and distribute Earth observation data. So if you are wondering how easy it is to access satellite images on EarthCache, alongside simple-to-use APIs, you can also quickly search through a location and specify the area that you are interested in, and then you can quickly search or order satellite images. You can also task a satellite in future to capture the data that you need for your application. So let me ask you questions. How many of you like to watch movies? OK, I guess all of you. So before I joined SkyWatch, whenever I heard about satellite images, I always thought about what's been shown in the movies, where government or government agencies and classified operations were the only one who can actually use the images. So growing up watching these movies, I always thought there is no chance for someone like me to do something like tasking a satellite or accessing satellite images. But when I joined SkyWatch, I realized the true potential of satellite images, which is not being only used by government or defense, but also how it can be used across various industries like oil and gas, agriculture, mining, insurance, government, smart cities, and the list continues. So we believe everyone should benefit from remote sensing data, and hence, data is important. For this session, I would like to focus on how we use geospatial data and how we process it at SkyWatch. So when customers order or search for satellite images, they specify something called as an area of interest, which describes the location for which they are actually ordering satellite images. Different vector representations like point, polygons, lines helps you describe location effectively. The one that you're actually seeing on the screen is actually a polygon data, which is a series of x and y, basically latitude and longitude, coordinate pairs that enclose an area. So our goal is to improve customer satisfaction by fulfilling as many satellite imagery orders as possible, which is also known as order fulfillment. So what is order fulfillment? It simply refers to how many requested orders were successfully processed and delivered to customers. Order fulfillment is really a big challenge in Earth observation. So let's try to understand why is it so hard. Tasking a satellite and capturing an image requires very precise planning and coordination. Usually, operators need to determine optimal timing to align satellite's orbit and its path with the target area to capture the image. And not only that, sometimes satellite images might not look as clear and show the information that you need because of the angle through which it captures the image. Okay, so let me give you an example. So imagine you're looking at a toy car on the floor. If you stand straight and look straight down, that's like a satellite with off-zero Nadir angle. However, if you move to a side and look at the car through an angle, you can see different properties of a car. This can also introduce challenges related to distortion and image qualities. One of the biggest challenges with fulfillment is also weather conditions. So 70% of the Earth is covered by cloud every day. So cloud cover is one of the major problems with satellite images. And it makes it really difficult for our customers to use and extract the information they need. With limited resources and competing demand, there could also be delays in fulfilling orders. So this leads to need of having proper prioritization techniques. So let's try to understand what are the different problems that we are trying to solve here. So first, we want to increase our order fulfillment to help customer get data that they want. And second, when we talk with satellite operators, the most common question that we get from them is, where should we focus? Where should we place our satellites? Where do we see demand from our customers? So this includes understanding of high targeted geographical areas, different customers requesting different data from different industries. And hence, we wanted to build a solution that can help satellite operators understand the actual customer demand and also help them with mission planning. To solve this problem, understanding 360-degree view of our customer demand was really important. So we had to answer these 4 questions: where, when, what, and who. So starting with where, we wanted to identify high targeted geographical areas where we see very high demand from customers. When indicates the seasonality of when certain customers request data. And at last, we wanted to understand what kind of data is being requested by which customers. So with every new product and feature, we always try to build an MVP version of it to see if it actually solves the problem that we are trying to solve. So the very first iteration that we built was just plotting the data and representing the area of searches and order events on a heat map, along with the ability to apply filters. I'm sure everyone in this room has seen this visualization in your dashboards or other application. So we also did the same. So there is nothing new here. So this gave us some ideas on customer demand, but it was not enough, and it was not scalable. And also, it's a manual process of understanding where do we see demand from our customers. So Heatmap did solve the issue of data visualization, at least as a part of V1. However, while working with vector data, which is in form of point or polygons, it is very hard to find patterns. And hence, clustering data was really difficult. Performing spatial joins across large data sets is expensive, and it's not scalable. Especially with the polygons, the complexity gets increased if you have complex shapes. To solve these challenges, we wanted to explore a simple and efficient way to represent and query geospatial data. And that's when we explored H3, which is a geospatial indexing system which was initially developed by Uber. So what it does is it basically divides the Earth's surface into hexagons. One of the cool features about H3 is that it is hierarchical. You can also see it in the first image that each hexagon can be subdivided into smaller hexagons. Each hexagon here has a unique address, which is called as an H3 index. Think of it like a postal code for a specific hexagon. The index is just a string or an integer number. So with H3, instead of representing a location in point or polygons, which is hard to understand, you can actually now represent data in array of strings or integers. There are also different different representations of geospatial indexing systems that are available to us. For example, we have geohashing, which is a grid-based indexing system, which makes use of squares instead of hexagons, and we also have Google S2. H3 resolution determines how large the hexagonal area would be. So the resolution value could be between 0 to 15. Higher resolution means smaller cells and more precise representation of an area, while lower resolution means larger cells and a more generalized view. So this gives us ability to zoom in and zoom out of map by using different resolutions. For example, we can start with a large hexagon that can cover whole country, and then zoom in into smaller hexagon that can cover a city or a neighborhood or even a street. So why H3 and why not any other indexing system? So instead of using squares or any other shapes, in hexagons, all the neighbors are equidistant, which provides a more balanced distribution of cells, which minimizes distortion and optimizes coverage. As with H3, instead of representing data in vector format, we now represent data in normal string or integers. So clustering data was now easier, and also with efficient data storage and retrieval. Instead of doing costly spatial joins, we can now perform simple join operations as we used to do in normal data pipelines across various data sets. Aggregations can be done on different resolutions depending on how large cell area we want. And lastly, Databricks runtime support for H3 was really a big advantage to us. Now, understanding H3 internals is really an interesting topic, but unfortunately, I would like to have to limit scope here for this session. So good thing about using Databricks is Databricks supports several H3 functions that you can use for analyzing geospatial data. For example, the one that you see on the screen, you can use this function to convert your geometry to H3 index. It basically takes two parameters. The first one is geography expression, which is just a geolocation represented in either GeoJSON, WKB, or WKT format. And the second format is actually the resolution, which is an integer value between 0 to 15. One of the benefits of using Databricks is that it supports 30+ Spark expressions that you can use to perform different tasks. Some of this provides really powerful capabilities like traversal, calculating distance between geographic points. You can also use these functions for use cases like route planning, proximity-based searches, finding neighborhood cells, and so on. So when I started learning about H3, I actually read a blog on how Uber uses H3 to solve some of their challenges. So to highlight some of the use cases at Uber, Uber actually uses H3 for efficient dispatching, which enables efficient matching of drivers and riders based on locations, which reduces the wait times and increase overall satisfaction. Dynamic pricing is also a really good use case here. So let's say once you understand the hexagon grid cells with high demand, Uber can actually adjust prices in real time, maximizing drivers' availability and revenue. Now let's deep dive into how we actually transition from insights to recommendations. Our first step was to simply aggregate data from multiple sources and bring it together in a single location. Sources include search events, order events, and other metadata. The next crucial phase was clustering and unification. Here, we calculate H3 index and unify geospatial data in a single format, which simplifies handling and processing and querying geospatial data. And then, to determine high targeted interest areas and find patterns, we perform anomaly detection based on customers' activity. And at last, once we know what area to capture at what time based on customer demand, we send those signals back to terrestrial satellite operators so that they can collect satellite images for us and ultimately increase order fulfillment. So how does all the components come together? At SkyWatch, we heavily use Databricks and AWS for our data infrastructure. In our high-level architecture, we store all the raw data in S3. For our data pipelines, we follow medallion architecture suggested by Databricks. It basically divides data processing into 3 layers: bronze, silver, gold. I'm sure we all have heard about it, and we all love it. So bronze layer stores all the raw data ingested from S3. For raw data ingestion, we also use Databricks autoloader to ingest and load new data as it gets stored in S3. So I highly recommend for everyone to check out how Databricks autoloader works and how you can use it for your use cases. In silver layer, we convert the vector data into S3 index, and finally, in the gold layer, we aggregate data on S3 index, that allows us to query faster. As you can see, all data is being stored in Delta format. I'll discuss about the actual data model and pipeline in the next slide. Now, once we have data processed and aggregated, as a part of data query layer, we use Databricks Serverless SQL Endpoint. So there were a couple of reasons on why we actually chose Databricks and using Lakehouse instead of using Snowflake or other data warehouses like Redshift and BigQuery. So all of our pipelines run on Databricks and use Spark for processing. And then moving data from one warehouse to another warehouse, one place to another place, is difficult. It's really challenging and expensive. Data warehouses like Redshift and others have really limited capabilities of geospatial data. With Databricks supporting 30+ Spark expressions, we can directly use those functions in SQL. And also, it is serverless, which is pay for what you use. So it also helps us with the cost saving and scalability. There are a series of steps that we need to take before actually sending the signals down to terrestrial operators. For this, we actually use AWS services like Lambda and step functions. Once we identify what areas to capture at what time, we send those signals back to terrestrial operators. So let's talk about the actual data model. So in previous slide, I mentioned we use medallion architecture. So let's try to understand the first bronze layer, which is the raw data. Over here, you can see event ID, event type, which can be search or order. We have geometry, which is the actual location of an area. And then we also have metadata. And we could also have other few columns attached to each event. From there, we generate S3 index. As a part of silver layer, you can see we add 2 additional columns. First is the S3 cells, which is an array of strings representing S3 cell IDs. And the other column is S3 resolution, which determines what is the resolution of the S3 cell, and which is an integer type. And finally, in the gold layer, we aggregated data based on S3 cell, S3 resolution, and date, and calculate cell statistics like total search event, total unique user count, total orders. So if you try to see the last table, now you can easily identify what S3 cell indexes have higher interest based on certain time. So let's actually talk about how we built recommendation engine and generated those signals. For this task, we adopted 100% serverless approach for cost and scalability. And hence, we make use of AWS services like Lambda and step functions. So for those who don't know what step function and Lambda is, step functions is basically a serverless orchestration workflow that is used to build distributed applications in AWS. And AWS Lambda is a serverless computing platform where you can run your code easily, and AWS takes care of scaling it. For this session, let's try to understand some of the components in the workflow. So first, we have search event anomaly detection and order event anomaly detection. So this actually run in parallel. What it does, it actually queries Databricks delta tables via serverless SQL endpoints. Now this steps actually returns us with the S3 cell where we see high interest, where we see high interest from customer demand. The next step is to convert S3 cells again back to polygons. So here we perform polygon intersections and identify the actual area we should capture image for. So at this point, we know what area to capture. However, we also want to check how likely satellite would be able to capture the image for a particular area given within a certain time. So this is where we calculate another metric, which is called probability of collection, which simply tells us like this is the probability of collecting this image between this time range. This makes use of, we make use of future weather forecast, satellite orbit path to determine probability of collection. Sometimes we may even generate many recommendations. And due to limited resources, satellite operators won't be able to capture all the areas. And hence, we need to rank those recommendations based on their importance and higher chances of getting fulfilled. That can lead to maximized revenue. And hence, to rank the recommendations, we also fetch user and industry profile, along with other parameters like probability of collection, cell statistics. We were able to rank those recommendations. And at last, once we have those recommendations, we store them in database so that we can use it for future analysis or usage. And then we send tasking requests directly to satellite operators. So what was the end product, and how does it look like? So let's say there was a surge in activity, and multiple customers are requesting data in one specific area. For example, there was a Canadian wildfire that took place, and we had multiple customers from different industries. They actually want to identify what neighborhood areas are being impacted by the wildfire. It is not necessary that every user specifies exactly the same AOI, but they are actually in the same area, as you can see. And they are also intersecting with each other. Using the architecture and data infrastructure shown in previous slides, we are now able to identify these important events by clustering them together and consolidate different AOIs in a single request, which could be easier for satellite operators to task a satellite and take photo of it, and also serve multiple customers at the same time. Overall, this new approach brings benefit to both customers and satellite operators. Customers now experience faster and more convenient access to satellite imagery, allowing them to obtain data that they need in a timely manner. And at the same time, satellite operators can optimize their operations, maximize their revenue potential, and efficiently manage satellite resources. So I would like to share our learnings during the development process. So first, optimization techniques like Z-order would really help to boost query performance. Depending on the data model that you use, you can actually apply Z-ordering on S3 cells alongside other columns. So if you don't know what Z-ordering is, it is an optimization technique which Databricks Delta has. What it does is it actually clusters data together so that it limits the scan, the query scan that it scans, and limits the number of files that it scans. So selecting appropriate S3 cell resolution is also really important for accurate data analysis. For Databricks customers, I would suggest you to plan and upgrade and use latest Databricks long-term support runtime clusters to leverage performance improvements. We have actually seen a lot of performance improvements and cost savings by leveraging the latest LTS runtime clusters. And at last, as with every machine learning or data analysis task, we have to remove noise in our data. In our case, users searching for really large areas, let's say more than 1,000 kilometers square, is mostly likely a noise and should not be considered while generating recommendations. So what are you building next with satellite images? And I hope this session would help you to use and process geospatial data and solve some of the challenges and build innovative solutions. Thank you. I think I've got a couple of minutes for questions, so.
Thank you. I think you mentioned vector database or vector index. Are you using that on Databricks or?
Okay, so for vector, what I meant was there's like different sort of geospatial data, which is vector data and raster data, right? Okay. So vector data, which is in form of point or polygon. So let's say latitude, longitude, right? So that's a vector data, which is, so let's say a customer search for a particular location that they actually need a satellite images. They actually specify something called as a polygon, which is area of interest, which is form of a vector data. And what we do is we convert those vector data into S3 cells.
And where are you storing your images?
So the images and everything is actually being stored in S3, okay. But the other metadata that we collect and the other user informations that we have, we make use of Databricks, and we store all the data in Databricks Delta.
Okay, thanks.
Any other questions?
Very interesting work. I was wondering how you decide on the zoom level for your data. Is it going to be uniform all over the data set, or you have different rows with different zoom levels?
Can you please repeat the question, please?
Yeah, on H3 zoom levels, how do you decide that in this project?
Yeah, I think that's a really interesting question and really important one. So for this project, it was really difficult task to like choose what S3 resolution, because there's like 0 to 15, and each resolution has average hexagonal area, right? So for this task, we wanted to, first we had to understand, okay, if we are capturing a satellite image from satellite, then how big a satellite can capture image for, right? If we are having S3 cell, which is, let's say, 500 area kilometer square, which is too large, but at the same time, we cannot have S3 cells, which is very too small, right? So for this project, what we did was we actually created index for different resolutions. So we found like there are 3 different resolutions where it would make more sense to index our data. So let's say it was resolution 3, 4, and 5, which is like 250 area kilometer square, which we thought was a sweet spot for us. And that's why what we did is we not only index on one resolution, we index on multiple resolutions, and also did partitions on the resolution so that when you query the data, it's efficient.
Thank you.
Hello. Yeah. You mentioned that fulfillment rate is one of the key metrics that you try to optimize for. Can you share what's the average range of the fulfillment rate that you're able to achieve?
Yeah, so for this, it's still in the beta version. So we actually haven't rolled out all these features in production to our customers. So I actually can't really tell about how fulfillment metrics actually went high by enabling this. But what this allows us to do is not only increase fulfillment orders, but also help operators to like build archive images, right? So let's say you are launching a new satellite and you don't have any orders, right? But so satellite is sitting up there doing nothing. If we know that if you are able to capture image for this area at this time, and there is higher chances of reselling those images in future, they can actually build up in the archive, and then in future, they can actually earn more revenue from them.
And you also mentioned about the probability of collection. So do you do any like price differentiation based on how difficult it is to like get the satellite image?
Yeah, that's a good question. So regarding probability of collection and pricing, So when we started EarthCache, the idea was simple. We wanted to make it easy and have consistent pricing per area kilometer square and based on the resolution, right? So we don't have dynamic pricing yet. So any customers who are actually wanting to buy satellite images from us, they have a consistent pricing. So we don't, if there is like higher probability, then we reduce the price and vice versa. So we don't do that at this time.
Thank you.
But that's actually the really good use cases, and like we have been talking like how we can actually use that in future.
Thank you.
Hi, can you please say a few benefits why you choose to use H3 and not GeoHash?
Yeah, that's a good question. So first, we had all the pipelines running in Databricks, right? And we had a lot of data, and we had to index and unify those data. Now, we could use geohashing, but with H3, first of all, there's like different advantages that H3 has. For example, all the neighbors are equidistant, right? Whereas in terms of geohashing, which is like a square type, a square shape, sometimes there is like a lot of distortion, right? And with the distortion, you can actually have inaccurate analysis of it. But one of the major benefits on choosing H3 was the support of Databricks that it has. With Databricks, let's say we are actually able to use H3 functions and actually query them directly in SQL, which we can't do that with geohashing, right? So that was one of the key reasons on why we chose H3.
Hi, so probably in continuation to that question, so do you think it would be any benefit of using maybe S2 instead of H3? I mean, forget about it, like, its usability through Databricks. Would there be any benefit of using S2?
Yeah, that's a good question. So I personally haven't explored how S2 works, so I don't know internals about it, but what I can say is how efficient and how fast we are able to calculate indexes with S2. That's something I would like to explore if I have to like decide on if we can use S2 for this task or not.
Another question, maybe someone else asked a similar question, but for those polygon covers, when you use H3 covers, those functionality, like, does it optimize for the H3 level? Or because I can imagine, like, sometimes, depending on the shape of polygons, different H3 levels can give you a better cover instead of like how much it can cover and how much it can miss. Is it something that you have to try and error to find, or there's this H3 APIs have this functionality to give you the best level?
Yeah, so I think let me try to like understand your question first. So with H3, and especially like how do we determine the correct resolutions, and does it give the proper analysis if you have like complex polygon shapes, and sometimes you have...
Yeah, because polygon shapes are different, so depending on your H3 level, you can like either miss a lot of the actual shape to give you like a, but it seems that there should be an optimization on what level to use to better cover it, right? So did you use it like, do it like manually, or there's this built-in functionality that this H3 API give you the H3 with, it gives you also, it would also return you the H3 level that was used to cover.
Yeah, so there is like few functions in Databricks. Let's say like I have index on resolution 5, right? And I want to like calculate and get cell indexes for resolution 4 or resolution 6. We can do that using those functions. But for this task, we actually haven't performed any A/B testing on what exactly resolutions we should use so that it accurately identifies whether the polygon shape has been covered perfectly or not.
Any other questions? Oh, of course, sorry.
Hey there, just a comment. This gentleman was asking about H3 functionality for covers functionality. H3 has a lot of different functions. For tessellating polygons, you can use polyfill, which has this, its methodology uses the centroid of the H3 cell, whether or not the centroid falls into the polygon's boundary or not. So that's how it determines whether or not to create one at the boundary. You can also use covers, which you showed here. Covers will fully tessellate the shape, which will have lots of excess H3 cell cover the outside of it. But yeah, there's more in the documentation that's provided on the functionality, but thank you for the presentation, that was great.
Yeah, thank you.
Any other questions? I'll just keep walking backwards. I think we did a full screen.
All right, thank you. Thank you all for being here, and thanks a lot for listening.
Thanks, Aayush.